Hello everyone, in this video we are going to learn about probability density functions of a random variable, and we are going to see a small example of it, and later on we will see future applications of it in the next videos. Okay, so let's say we have a random variable x and we denote a probability density function for x, and we denote it using this manner, using small f of x. So this is the usual notation for it, and it is defined as the differential of the cumulative distribution function capital F of x of small x, and we take the differential of it with respect to small x, and by doing this we get something known as the probability density function. So probability density function will basically give you the density of a random variable, the probability density of a random variable x. So what does that mean? Let's say I want to find out the probability of my random variable x lying in a range from a to b. So this density function is going to be really helpful for finding out such things. All you have to do is you have to integrate the probability density function of x from the range of a to b. And if you find out this value, this will give you the probability of a random variable x lying between this range. Or you can also do this. If you don't know the cumulative distribution function, you can also do this. Let's say b is greater than a. So this would also give you the probability of a random variable lying in this range. Now let's see a small example of it. So we had seen in our previous video that we were doing a coin toss experiment, and it was an unfair coin, as we can see here. And in this example, the sample space of the experiment was heads and tails, as there can only be two outcomes, and the probability of getting a heads was 0.6 while the probability of getting a tails was 0.4, and the random variable took the value of 1 when the outcome was heads, and this random variable took the value of 0 when the outcome was tails. And we had defined a probability space for it, and we had proved that this was a valid random variable, and we had also found out the cumulative distribution function of this random variable x. So the cumulative distribution function was this. Now we are going to use this cumulative distribution function and differentiate it with respect to small x to find out the probability density function of this random variable x. Let's do it. So this is my cumulative distribution function capital F of x of small x, denoted like this. Let's say if I differentiate it with respect to small x, what would we get? So from minus infinity to 0, we know that the slope is 0. So the value of the probability density function would be 0. And there is a spike here, as you can see, at x equals 0. So you can say that I'm denoting it like this here. Then again the slope is 0 between the interval 0 to 1, and there is again a spike at x equals 1. So you can say that this is a Dirac delta function denoted by this, which means that the cumulative density function fx of 1 would be 0.6 and fx of 0 would be 0.4. So you would need a Dirac delta function if you want to represent it in a continuous space, and if you want to use the notations of probability density functions. But in case of discrete random variables such as x, we can also use something known as probability mass function. So it would be a same function as this. It's just that since x is a discrete random variable, we are going to use this notation. And we have seen that small f of x, which is the probability density function or the probability mass function in this case, would have the value of this. So it would take the value of 0.4 when x equals 0, and it will take the value of 0.6 when x equals 1. And you can see that it does denote the probability of the outcome of the experiment being heads or tails. As you can see, the probability of getting heads was 0.6, and the random variable took the value 1 when the outcome was heads. So you can say that fx of 1 was 0.6, which is the which is the probability of getting a heads, and fx of 0 was 0.4, which is the probability of getting a tails when the random variable took the value 0. So we can see that intuitively it does correlate with the probability of our experiment, of our event occurring. Now let's see an example of the usage of probability density function and the cumulative distribution functions. Let's say we use the same random variable x and we want to find out the probability of our random variable x lying between 0.5 to 1.5. So what does this mean? We know, as we know, that the cumulative distribution function denoted by this is nothing but the probability measure of the pre-image of a random variable, which was a measurable function from the sample space to the real line. It is also denoted by this. So cumulative distribution function capital F of x is also denoted by probability of a random variable having the value less than small x. Now in this case, if you want to calculate the probability of a random variable being in this range, you can easily do it in this way. So we know that the probability of x less than 1.5 is basically the probability of our small x being from 1.5 to minus infinity. So this is this, and this is fx of 1.5, and we know the cumulative distribution function, this can be represented in this way as well. This is minus infinity and this is 0.5. So the probability of a random variable being less than 0.5 is this one, and the probability of a random variable less than 1.5 is this one. So if we want to calculate the probability of x between these values, all we have to do is we have to subtract both of these. So this is 1.5 minus fx of 0.5, and this is the answer for it. So if we want to find out the probability that the random variable x is lying between this range, the probability would be this. And in some cases it is very difficult to determine the cumulative distribution function of a random variable. So instead of that, we use probability density function to calculate the same result. And as you know, that probability density function is nothing but the differential of this cumulative distribution function. So it can also be denoted in this way. So in this example, we know that if we integrate 0.5 to 1.5 and fx of x dx, we know that this will take on the finite value only when x small x equals 1, and the value of small x being 1 is, this is 0.6, hence this value will be 0.6. And we can verify it from cumulative distribution function as well. This value was 1, this value was 0.4, and 1 minus 0.4 is 0.6, and both of these match.